Hello everyone and welcome to Refined Chemistry YouTube channel. Following the students' requests for me to have a channel, I've decided to venture into this, and I hope it will be helping you improve in your mastery of content and improve your grades, that is. So I will be concentrating on IGCSE and A-level chemistry, and I hope you'll be able to enjoy these tutorials. So to start off today, we're going to have a few questions from Igcse chemistry, that is Edexcel exam board. So as you can see, the first question is on the preparation of zinc nitrate crystals. And of course, we've been given the procedure there. And I'll want us to go through the procedure before we tackle the questions for us to lay an understanding of our previous concepts. So as all of you know, before you tackle any question involving salts, it is good that you understand the solubility of salts first. So all the nitrates are soluble. We need to have that in mind. So let's just go through the procedure. We have 50 cubic centimeters of dilute nitric acid, which was poured into a beaker, followed by the addition of zinc powder to the acid. Zinc powder was added until it was in excess, then filtered after. Then finally, the crystals were obtained from the filtrate. Of course, you know we have a process to follow after we've received our filtrate. So then we can actually go to the questions directly. Let me just scroll down. That is our first question, A. State why the mixture is filtered. As you can see, initially, we added an excess of zinc powder. So the mixture was filtered to remove the excess zinc. So you can write to remove excess zinc. So to remove excess zinc. That is good. So then the second one, we are supposed to describe how a pure dry sample of hydrated zinc nitrate crystals could be obtained from the filtrate. Now, this is where your understanding is required for us to come up with that procedure. So the first thing that you need to do once you have a filtrate, since this is a soluble salt, is to ensure that we heat that filtrate until we reach the crystallization point. So you can say heat the filtrate until the crystallization point is reached. Another question you need to expect from this part is, do you know how to check whether the point has been reached, the crystallization point? You can always check this by dipping a glass rod in the filtrate, exposing in the air for it to cool. Then if you see the crystals, you'll be able to say that the point has been reached. Then you can proceed with your process. Anyway, if the point has been reached, then we can do something else. So you leave the solution to cool. So you need to leave the solution to cool for those crystals to form. So after the crystals are formed, now remember, if you do this in the lab, wherever you're going to go for your crystals, most of the times not all the solution has crystallized. So you may want to do the second filtration to remove the excess solution. So you can say filter to remove excess solution. So basically, removing the excess solution means that we are going to obtain your wet crystals. So now we have our wet crystals. So what do we need to do next? We need them dry. So we need to put them in a warm oven to dry. Put the crystals in a warm oven to dry. So those are the 4 points you need for you to score all those 4 marks. Now, please note that it's good that at least you mention 1 apparatus or equipment you are going to use in the lab. So that question is done. So most of the time when you see a lot of space given, it doesn't mean that you need to fill everything. You only need to put the right content over there. Part C. This equation represents the formation of hydrated zinc nitrate in the experiment. And of course, you see, it's going to have water of crystallization. That is why we say it's a hydrated salt. So in another experiment, 9.75 grams of zinc is completely reacted with nitric acid. Show that the maximum possible mass of hydrated zinc nitrate that could be formed is approximately 45 grams. We've been given the relative formula mass of that is the hydrated zinc nitrate, which is 297. So for you to get the maximum possible mass, remember maximum possible mass, you can use your stoichiometric equation, use the mole ratios, and that is it. So what do we need to do? So the first thing that we need to do is to actually get the number of moles of zinc, which we can do here. So we can say the number of moles of zinc. When I write N, then of course I have brackets zinc. That means I want to find the number of moles of zinc. So what does that mean? We have the mass of zinc, of course in grams, divided by the molar mass, which is I think 65, if I'm not wrong. So molar mass, which is 9.75 divided by 65, which will be, so let's just work out it together. 9.75 divided by 65, it turns out to be 0.15 mole. So now we do have the number of moles of zinc, which are 0.15 mole. Remember, we've been told to try and show that they approximately prepared 45 grams. So what we do, for you to get the mass of zinc nitrate crystals, we use the mole ratio or the molar ratio. So you can see over here it's 1, and also here it's 1. So it's basically 1:1. So that means these moles will be equal to the number of moles of the hydrated salt, which will be 0.15 mole. So for us to get the mass, so mass will be equal to mole, which we already have, times molar mass, which we have as 297. So it will be equal to 0.15 times 297. So that turns out to be, we can work it out, so times 297. Great. So it's actually coming up to 44.5, which, as you can see, it's very close to 45. So our answer must be correct. That is good. So then we can proceed to the next question, which will be finding the percentage yield of hydrated zinc nitrate crystals. So as you remember, we can easily find the percentage yield, and remember the percentage yield will be equal to the actual yield you divide by the theoretical yield, you multiply by 100. So the actual yield is the yield or the amount of a substance that you basically get when you go to the lab, do the experiment, weigh your product, and record a value. That is what we call the actual yield. The theoretical yield is the mass or amount that you can get by just using an equation and calculating without going to the lab, that is. So according to this, we do have the values. So it's just substituting them and then we are done. So we have the actual yield we've been given, the value is here, 36.4. So we say 36.4 divided by 44.55. You multiply by 100. So let's just compute it. We have 36.4. You divide by 44.55. Then we multiply by 100. So our answer turns out to be 81.7059 and so many decimal points there. So what we do, we can actually give our answer to one decimal place and it will be 81.7%. So 81.7%. So we are done with that question, and you can see if you manage to solve that whole question, you will get all your 9 marks. So moving to the second question for today. This question, of course, involves a scientist who uses these apparatus in an experiment to reduce a metal oxide to a metal. Most of the times we use this process when we want to, come up with the empirical formula of a certain metal oxide. So you can see, before even we go to the question, the scientist is actually passing a stream of hydrogen through a tube into a metal oxide that is being heated. And at the far end, there is an opening where the excess hydrogen is being burned. So then we can see what they were doing here. Before heating, the mass of the empty tube and the mass of the tube and the metal oxide are recorded. So first of all, they recorded the masses of the apparatus mentioned. So after heating, the tube is allowed to cool and the mass of the tube and its contents are recorded again. So part A, state why the reaction of the metal oxide to form a metal is described as reduction. Now, there are two ways in which we can describe reduction. One of them is in terms of oxygen transfer, the other one in terms of electron transfer. But I will advise you to make it easier for you that always look at the nature of the question. This question is involving oxygen here. So you can see metal oxide. So it means metal and then oxide is here. So it's better for you to go to the route of oxygen transfer. So state why the reaction of the metal oxide to form the metal is described as reduction reaction. So reduction is basically the loss of oxygen. So we can be specific and say the metal oxide, the metal oxide loses oxygen. So the metal oxide loses oxygen. So basically, this is an act of reduction. So we've answered the question. The second question, state why it is important to relight the hydrogen at the end of the tube if the flame goes out. So remember, hydrogen is highly flammable. So to avoid an explosion, it's better for you to relight it to ensure that there is no explosion. So you can say to avoid an explosion as hydrogen, sorry for that. So as hydrogen is highly flammable. Hydrogen is highly flammable. So you don't want to have an explosion, so it's good for you to relight that flame. The third question. So explain why it is important to continue passing the hydrogen into the tube and burning the hydrogen at the end of the tube until the contents have cooled. Now, please note that the main aim of the experiment was to reduce the metal oxide to get the metal. So after you've completed the experiment, you need to keep passing the hydrogen to ensure that no oxygen comes into the system. Because then if oxygen joins the system, then it's going to oxidize your hot metal back to an oxide. You'll have done zero work. So it's okay for you to say to prevent. So you need to keep on passing your hydrogen gas through that tube to ensure that no oxygen joins the tube, because if oxygen enters very quickly, it will react with your hot metal to reform the oxide that you had actually you had initially. So to prevent oxygen from entering and reacting with the metal, reforming the oxide, the metal oxide. So that is the main reason as to why we don't let oxygen to enter. So we keep on passing hydrogen gas until the setup becomes very cool or cools down. So we go to the next part 4. Describe what should be done next to ensure that all the metal oxide has been converted into the metal. Now, just through the appearance, you'll not be able to tell whether the reaction is complete. So the first thing you need to do, or the only thing you need to do, is to reweigh the apparatus. So reweigh the tube and contents. Okay, so you need to heat, and reweigh the tube and contents until constant mass is reached. Now I'm going to explain why you need to heat again. So you can actually say heat again and reweigh the tube and contents until constant mass is reached. Now let me just show you why that is important for you to know whether the reaction is complete or not. Let's just go up a bit. Now, when you pass hydrogen, it actually removes the oxygen from the metal oxide. So as time goes by, the mass of the contents will be decreasing. So for you to know that the reaction is complete, you'll have a constant mass. The mass will not change. So that is why you need to reheat, keep on weighing until that point the mass becomes constant or remains unchanged. So now we can go down to our rest of to our answers. To our questions. Good. The second part. In this experiment, a mass of 4.14 grams of metal is formed from 4.46 grams of metal oxide. So we are supposed to calculate the amount in moles of oxygen atoms in the sample of the metal oxide. So how can we get the amount of oxygen atoms? So first of all, we have been given the mass of the metal, which is 4.14. Then we've been given the mass of the metal oxide, which is 4.46. So it is very simple for us to do this. So for you to get the mass of oxygen, you need to subtract the mass of the metal from the oxide. So that will be 4.46 minus 4.14, 4.14. So the mass, the first thing before you find the moles, actually find the mass of oxygen atoms. So mass of oxygen atoms will be equal to 4.46 minus 4.14. This turns out to be 0.32 grams. Good. So then how do we find the amount? The amount in moles then will be number of moles will be equal to the mass, which we already have, which is 0.32. You divide by 16. So a reason as to why we are dividing by 16, we are actually dealing with oxygen atoms and not the gas, because the gas is in molecular form, that is. So we do have that. You divide by 16, and our answer turns out to be 0.02 mole. It's good that you understand what the question requires you to do, because most of the students here will divide by 32. Please remember that we are dealing with oxygen atoms. Good. So then we can go to our second question there. The formula of the metal oxide is MO, where M represents the symbol of the metal. Deduce the amount in moles of M in the sample of the metal oxide. So there is one thing I want you to see. So this is the formula of the oxide, and the M is actually representing the symbol of the metal. So for you to have this formula, it means that the mole ratio of your metal to the oxygen atoms is 1:1. Or maybe you can say the number of moles of the metal and oxygen are equal or are similar. Why am I saying that? Remember, anytime we are calculating the empirical formula, for example, we will say M, that is our O. So if you do have, for example, 0.02 mole here and you have 0.02 mole here, of course, you'll divide by this lowest number of moles, which in this case happens to be 0.02, actually the same. So this is the only time you're going to get MO, because then the mole ratio will be 1:1. So by the fact that you've been told the metal oxide has a formula of, MO, it means M has the same number of moles as oxygen atoms. So here you don't need to really have any calculation. So this was just to remind you, so that you can think properly along those lines. So basically, we have the same number of moles we had above, which are 0.02. Then we are actually supposed to find the relative atomic mass of M. So then how do we find the relative atomic mass of M? Okay. For you to find the relative atomic mass, you can use that triangle, which I think most of you are used to. You can make use of this. It's a very simple thing. You basically don't need to do it if you are used to moles, but I think if you're new to this one can be helpful. So what are we supposed to have on the upper triangle? Here we are supposed to have the mass in grams. Then of course you can have your mole here. Then you can have your molar mass. Remember, molar mass in this case is the same as the relative atomic mass. So that means if we want our molar mass, it will be equal to the mass of the metal divided by the number of moles of the metal. So that turns out to be, we can go up and check the mass of the metal because we were given, it's over here. So which turns out to be 4.14 grams. So we can go down and say 4.14 grams, 4.14 grams divided by the number of moles, which is 0.02. So this one turns out to be, let's see, you can work out that one. So 4.14 divided by 0.02. So which is exactly 207. So that is it. The only knowledge that you are supposed to retrieve is on how you can find the molar mass. The molar mass in this case is the relative atomic mass of that metal. So this triangle might be helpful. That is good. Our last question for today: use the periodic table to identify the metal M. So this one you can do it. You can go to the periodic table and check the element or an element that has a relative atomic mass of 207. Now, please, when you're going to check that one, let's say our element is M. We are not saying that this is the symbol for that element, just a representation. So you are going to read this value you find here. So please don't read the value down here, because down here we have the atomic number, which is the same as the number of protons. So when you're going to read there, this is where you're going to read. So check the element that has this, relative atomic mass to be 207. So as you may check later in the periodic table, it will be lead. So you can say it is lead, and that is it. So for today, we will be stopping there, but be prepared to have the notification on, because I'll be uploading a very good tutorial videos on IGCSE chemistry and A-level chemistry. You will be able to sharpen your question answering skills, and I'll be able to guide you all through. Thank you so much. See you in the next video.